So in this video, we're going to do a review of conductors and insulators, but this time instead of looking at it from thermodynamics or from a heat standpoint, movement of thermal energy, we're going to look at it from moving of electrical energy, so how easily it works. Honestly, the same rules apply for conductors and insulators as in thermodynamics. It's just we're looking at it from a slightly different perspective. And then we'll see how conductors and insulators work into the idea of lightning as well. So first, let's talk about insulators. Insulators are substances that do not allow charge to move easily from one area to another. And so just like with thermodynamics, you can't stop charge from traveling. What you can do is slow it down. If enough charge builds up, no insulator will be able to stop that charge from moving or cause that electrical energy to move. So it's slowing it, so not travel easily. Examples are exactly the same as in thermodynamics: glass, dry wood, plastics, cloth, rubber, dry air. And notice here how we're saying dry. Whenever water is involved, water can help conduct electricity. So this is slightly different from thermodynamics, but the ideas are still the same examples, but now we'll see how water can kind of play into allowing this energy to move. So conductors have loosely bound electrons, and so what material is a good conductor? Metals. Metals are excellent electrical conductors. So electrons carry the charge through the metal. And so it's either going to be, and we'll look at this more in current electricity, but electrons either carry energy or the charge is actually the electrons themselves. So metals easily allow electrons to move through the material, thereby moving electrical energy and electrical charge, because the charge comes from those electrons. All right, so now let's talk about how conductors and insulators work with lightning. Lightning happens in storms first because the wind rubs the surface of the ground and the buildings. And so here you'll see the blue. The blue is the wind. So it rubs the ground and it pulls the electrons from the ground up into the sky. And so if you look really carefully, you'll see the negatives coming up here. That means the ground becomes positive. If it loses electrons, you lose mass, so you become positive. The clouds, especially the bottom of the clouds, become negative because that wind carries the electrons up. So you gain electrons, you become negatively charged. Now, a little side note, this is what we call potential. There's potential for these electrons to move. And so whenever you have this difference in charge, there's potential for those electrons to come back to the ground. If enough electrons build up, then it comes back down in the form of lightning. And that's where you see it striking. Now, some clouds may hold more electrons than others. So the cloud here might be very negative, and the cloud here might be just a little bit negative. And so that's how you can get that arcing of lightning from cloud to cloud, because these electrons want to move to where there's less electrons. So here's a video showing an airplane getting struck by lightning, and this actually happens more commonly than you imagine, but airplanes are actually built to withstand lightning strikes. So whenever the lightning hits the plane, it just goes through the plane. So everything is nice and insulated for this type of reason. Static electricity always takes the shortest path. And so we talk about energy, especially electrical energy, heat energy, is very lazy. So if you want to write that down, like beside the notes or whatever, and just talk about how energy is lazy. And so it always wants to go the shortest path. Here, the shortest path to the ground is using the airplane to get to the ground. And so here's the same picture in slow motion. What you'll see is the lightning hits the front of the plane since it's closer, and then it comes out the back of the plane. And again, everyone inside is perfectly fine. The electronics inside are perfectly fine. The difference is that there's nice insulation within the plane to keep it running just fine. And so what lightning rods are supposed to do is actually give that energy a path to go on. So lightning rods serve two purposes. One is to prevent lightning from even happening. And what it does is it allows a short distance, for like Stone Mountain or some of the really, really tall skyscrapers, it allows a short path for those electrons that are built up in this cloud to jump. And if it's a small enough gap, it loses that energy and you don't actually get lightning. The second purpose of lightning rods is to predict where the lightning will strike. So it hits a lightning rod, and that lightning rod has a specific path to the ground so that the buildings, the towers, things like that, will not be affected by lightning. Without any of these, then lightning, the energy builds up, and when it's strong enough, it actually strikes.